So in the last class, we defined what are vector spaces, right? And if some of you do not recall what is a vector space, please raise your hand without any hesitation. We will go over it again. Yeah, thank you. What's your name?
Aditya.
Thank you, Aditya. So a vector space V we call V a vector space if it has two properties. The first is that V is an abelian group. Okay. Now again, this term, abelian group. Please raise your hand without any hesitation if you do not recall what an abelian group is.
I was not present.
Okay, no problem. We repeat what an abelian group is. What's your name, by the way?
Ashish Patel.
Ashish Pandey. Okay. And how did you break your?
Like my friend, like Paul.
Oh, I see. I see. Oh, I hope this gets honored soon, because you cannot take notes also, or you cannot write it right under. But the lectures will be online, so you can check them if you attend the classes. Please write your name there. V is an abelian group if let's define what a group G is. So it should satisfy three properties. One is, well, actually, you know what is a set, right?
Yes, sir.
Okay. So suppose G is a set. Okay? So a set with three properties. Well, a set with a law of composition, that is, you take two elements from G, a set with a law of composition. This law of composition will be called group law. And if your G is a group, so and it will be denoted by some star or plus or some operation. Okay, what it means is right. That is, if G1 and G2 is in G, then G1 star G2 would also belong to G. If you have any doubts, please ask me and not your friend, because there is a humming noise in the class which may disturb others and myself as well. So G1 and G2, if there are two elements in G, you compose them. That is, what this group law is. The group law is a map from G cross G to G. That is, given two elements in G, your G1 and G2, say a pair of elements in G cross G actually, the Cartesian product, you are mapping them to some element which you are denoting by G1 star G2. So whatever law of composition is, you can compose two elements in G to give another element in G as well. Okay, so G is closed under this law of composition. Moreover, this law of composition should satisfy three properties. Okay? The first one is, we are still defining what is a group. So G, a group. Well, it's better to write G star here because we are going to consider some properties of this star. So the first one is associativity. The second one is identity, and the third one is existence of inverse. Just call this inverse. Okay. So we are going to define what these properties mean. Associativity is quite simple to see. That is, suppose suppose G1, G2, and G3. Suppose G1, G2, and G3 are elements of your group G. Okay. Then G1 star G2 star G3 is the same as G1 star G2 star G3. Okay. That is, it doesn't matter in which way you compose three elements. That is, whether you do this first or this one first. you always get the same outcome in G. Okay? And identity just means that there exists an element I sub G, say, in G, such that if you compose it with any element of G, say G is a random element in some element in G, okay, such that for all G in G, G star Ig is equal to Ig star G, which is giving you G. And then the inverse, that is, for all G in G, well, you would ideally like to denote the inverse of G by G inverse, okay? But still now, I mean, we are talking about an element G in G, but before we denote, I mean, define inverse, we cannot use this notation, right? So we just say that for all G in G, there exists some G dash in G such that G star G dash is equal to G dash star G is equal to the identity element. Okay? And actually, from the associativity of the operation, you will see that if there exists, I mean, suppose G dash and G double dash are left and right inverse of G, then using associativity you can show that G dash is equal to G double dash. You have seen the uniqueness of inverse of square matrices, right? If there exists a left inverse and there is a right inverse, they should be equal, because you can write these matrices A, B, C. I mean, suppose A is a left inverse and C is a right inverse of the matrix B, and then you have this is equal to AB times C, right? And since we are saying that this is a right inverse, this will give you identity, and this will give you identity also because it's a left inverse. Okay, so this one would be just A because this is identity, and this one would be just C because this is identity, and then you get the left inverse is equal to the right inverse. Okay? The same for an arbitrary group because you have associativity. All right. Now we have defined what a group is. So group is just a set with a law of composition such that these two properties are satisfied. Okay? Now what's an abelian group? It's just a special kind of group where this operation is very simple. That is, here we said that it's operation in G1 star G2, but note that for a general group, this may not be commutative. That is, G1 star G2 may not be equal to G2 star G1. For example, take the group of invertible matrices. Okay. Okay. By the way, I have not introduced this group in any of the earlier lectures, so let's write it down. Have you seen this notation earlier? GLN, R or C or whatever field there.
Yes, sir.
GLN. Okay. So this is the general linear group of matrices, of invertible matrices with elements from of invertible matrices with entries from R. Okay. You could have replaced this R with C or any other field. You're coming to define a field. I think you would, I mean, since you have not seen what a group is, I mean, fields, I'm not sure whether you are, you know what a field is?
Yes, sir. From previous lecture.
Okay, all right. So, but nevertheless, GLNR is a notation for the group of invertible matrices. Group in the, okay, Vishesh, you had something to ask?
Yeah,
Vishesh, right?
You just cleared it.
Okay.
You cleared me.
Okay, thank you. So, this is the group of invertible matrices, and here the law of composition is product, taking product of two matrices, okay? And Also, we denote all the n-crossing matrices, irrespective of whether they are invertible or non-invertible, by this notation, which we introduced in the last class, in R. This is a set of all matrices, all real matrices, real n-crossing matrices. Okay, so this is one group, this is another group. Yeah.
What does general linear refer to?
Okay, it's just a name of the group, general linear group. Okay, this is by GLNR we just, well, actually this is a group of linear transformations. We'll say linear operators actually from an n-dimensional vector space to an n-dimensional vector space. And I mean both of, so linear transformations are like, so for the moment we are learning about vector spaces, and then linear transformations is a map from a space, a vector space to another vector space, like space flight. Okay. Yeah.
Sir, you said that in a group it can't be commutative. But in an inverse definition, you are using the commutativity like G grows the definition.
No, I'm not. I'm not using commutativity here. That's why I'm writing it in both ways. But I'm just saying that this is superfluous. Because of associativity, it's fine if we just write G star G dash is equal to identity. Because if there exists a left inverse as well, then they should be the same. Now, yeah. So both these groups, there's a difference. This is a multiplicative group, right? It's defined with respect to multiplication. And this is a group as well, but it is the additive group of matrices. You can add two matrices, n-crossing matrices with real entries to get another matrix with real entries. Okay. And note that in this one, if you add two elements, say A and B, two elements in M and R. Okay, and then A plus B and B plus A, are they the same?
Yes.
They are. Okay, because you are adding them entry-wise. Okay, and I mean the real addition of two real numbers. It doesn't matter in which way you add them, you get the same thing. Well, now suppose you get two matrices in GLN. Okay. By the way, since you are seeing the definition of group for the first time, I guess because you missed the first class. So can you tell me what is the identity limit here? M and I. This one.
Identity element will be B for B minus A or A minus B.
That is I think you are referring to the inverse. So for A plus minus A is giving you 0. So 0 is the identity element. 0 is the additive identity in this one. Okay. This is an additive group, and this kind of group where it doesn't matter, you can see that. And your name again once more?
So Ashish.
Ashish. Thank you, Ashish. So if this, what I want to say is that if it doesn't matter in which way you use the law of composition, that is whether you compose A with B, A composed with B or B composed with A, if they are giving you the same output, then you say the group to be commutative or abelian. So that is the definition of an abelian group. That is, in an abelian group, I think we can use that board. Coming back to what I was going to say about GLNR, but let's just give the definition of abelian group since we are in a flow. Okay. So what we want to say here is that G is an abelian group or a commutative group if G1 star G2, well, here we of course mean G star, G given with the operation star is equal to G2 star G1 if it commutes. And if this operation is commutative, we call it an abelian group. Alright, and now an example of a group which is not commutative. We have written it down on the board. Can you see?
Yes,
GNR, right? Because matrix multiplication is not in general commutative. A times B is not equal to B times A. You can take two cross two matrices, and I think you have seen such examples in the previous course already. So example of an abelian group. IISER, example of an abelian group, except MNR. Just try to give any example. Yes. Wait a minute. It's like this one. So at first, give an example of a group. We will later think whether it is abelian or not.
Symmetries of a triangle.
Symmetries of, yeah, sure. Symmetries of a triangle, you mean, right? Okay. So yeah, well, I should not draw it. Sorry. Take the equilateral triangle, the simplest kind of structure, and then what are its symmetries?
It can rotate 120 degrees.
It can rotate, right? So how many rotations?
2 times.
And what are the rotations?
So 1 by 120, 1 by 240.
A, B, and C. And then where can we map A in the rotations that you were talking about?
We can map A to B.
Yes, or
A to C.
or
Or A to A.
very good. So how many rotations then?
3.
3 rotations, right? And note that this rotation, if you repeat, that is A to B, and then you repeat it again, so rotation by this angle,
It's
120 degree, right? So if you call this rotation R, repeat it twice. That if you take R composed with R, you can call it R square. If you are just denoting the group of rotations, you can also denote it 2R. It doesn't matter whether you write R plus R or 2R, or R squared. And then what we're getting, I mean R, so if R is this, then R square will map A to C, right? What will R cube do?
A to A.
Into A. So R cube is actually the identity. Is there any other symmetry except the rotations? Yes, Moni? If you flip it, in I mean on which axis?
About y-axis.
Okay,
Y.
that is by the line of symmetry. You want to make a particle line of symmetry. Yeah,
We can flip it any ways.
exactly.
From B and C.
From C or from this. All right. So now this is a group, but nevertheless so these are like the reflections, right? So reflections on rotation and reflection both starts with R. So let's denote the reflections by capital R. Okay. So maybe this one R1, this is R2, and this is R3. Now, for the group to be abelian, what do we require?
Like we rotate this way and this way, this lane.
Well, rotation is a commutative group because if you just consider the group of rotations, it doesn't matter. As we said that you can denote it. You can write it multiplicatively or additively because it doesn't matter whether because actually all the rotations are just powers of this or multiples of this. Okay. Whereas reflection is something else. Okay. Reflection on the axis are not by a particular rotation because these two are getting extended, whereas this is remaining fixed. In rotation, none of the vertices are fixed unless it's the identity rotation. Okay. So, and by the way, what happens if you apply R1 twice?
We get a map A to C and C
It's,
to
you
B
get identity because
twice.
yeah, you're applying it twice. That is R1. So at first when you apply, B remains fixed.
Oh,
A comes to C,
yeah.
C comes to A, and then you apply it again. So C comes back to the original position of C. A goes back to the original position of A. Okay. So for each of these reflections, we get that R1 squared equal to R2 squared equal to R3 squared equal to identity. Okay. Repeat any reflection twice, and there is no change to the original picture. Okay. So now, what's the question you should ask for showing whether it's an abelian group or not?
Whether R1, R2 and R2, R1 are same, like it maps to the same.
R1, R2. Let's check whether it does. R1 composed with R2. You said, right? This is not quite equilateral. Isosceles, I would say. Okay. So we were denoting R1 reflection on this one, right? And R2 we will give a name. R2 was this one. So reflection on this axis, right? Okay. And now call this A, B, C. So let's see what happens. A goes to C, right? B remains fixed. So if you apply R1 to A, this, okay, let's write it down like this. R1 of A is equal to C, R1 of B is equal to B itself, R1 of C is equal to A, right? Now let's apply R2. So R2 of A is giving you B, and R2 of B is giving you C, right? And what is R2? Any doubts? Excuse me. Your name, please. Your name. Yes. Yeah. Bitan. Okay, Bitan, what is your doubt? You are asking something to him? What are you doing? You are not looking at the board, you are talking to him. What about what? Do you get what is going on the board? I mean, do you have any difficulty with that? Okay, so then perhaps you can tell me what are the images of R2. I mean, if you compose this with R1, let's do this exercise then. R2 of A is B, R2 of B is equal to C. What is R2 of C? R2 of B would be A. Okay, thank you. And then R2 of C? C, right. R2 of R1 of A, this would be R2 of C, which is C, right? Now R2 of R1 of B, R2 of R1 of B is what? R2 of B, and that is equal to A. Okay, and then R2 of R1 of C, which is equal to A, that is, then you apply R2 of A and you get B. Okay, and now we do R1 of R2. Okay, R1 of R2 of A was what was R2 of A again? We wrote it down somewhere here, B. So this is R1 of B, and what is R1 of B? That is just B, right? And R2 of C, okay, this is R2 of C is C, and you are now applying R1 on C, and you get A there, right? And then you apply R1 on R2 of B. Well, what is R2 of B? That is A, and then you are applying R1 on A to get C. And And now let's compare the images that we got. So this composition R2, R1, this is again in the set. It is not going out. So this is a binary operation on the set. That is, you are taking two elements from here and here, you are composing them, and then this is your matrix. Okay. So A is being mapped to C, and C is being mapped to B, and B is being mapped to A. Okay. All right. So this is again this is a composition of reflections, which is giving you a rotation. Okay. And then if you look at the other one, this one, this is also a composition of reflections, which is going to give you another rotation. And these rotations are not the same. Aditya, you managed to give quite an example with which we spent almost the entire class, but nevertheless it's not an example of an abelian group. So give me an example.
Integers for
Yeah?
integers for addition.
Yes, integers under addition.
We
See,
can
if you
just
add
drop
two integers,
the
yeah?
reflections, right?
Reflections?
If we drop the reflections,
Perfect. Yes. Thank you, Sunny. So this is a group of. If you just take the rotations, then it's a commutative group, right? Because it doesn't matter. It's a power of the same rotation. Okay? And it has in fact something to do with the group of integers as well. Because you see, every integer you can generate it with 1, right? So 1 plus 1, that is 2, 1 plus 1 plus 1, that is 3, 1 plus 1 plus 1 plus 1, that is 4. And also take their inverses, and you get the negative numbers. So it's so these kind of groups are called a cyclic group. Okay? That is, which are generated by a single element. So it's entirely with the definition that we spent this class. But nevertheless, at least I hope it is clear to you, Ashish, what is an abelian group in which the operation is commutative. And a vector space is not just an abelian. Let me write down the other defining property, that is scalar multiplication. And that means, you said you know what is the field, right? So suppose F is an underlying field. It could be R, it could be C, it could be some other kind of field. So from F star B to V, there's a map, and this would be called scalar multiplication. That means it's kind of, well, it's a little bit generalization of what you have seen in vector spaces like this, where you have, say, AB, 2 cross 2, set of tuples of 2 cross 2 things in R2, say, and you multiply this with another real number to get some A dash and B dash, also elements of R2. Okay? And there are some properties like associativity, distributivity, and if you multiply in particular with 1, that is the identity element of the field, you get this one back. Okay? And associativity just means that A times some elements, say alpha times B times this, is beta times, alpha times beta times this would be just beta times this times alpha times this. Okay? And distributivity would mean that if you add two vectors multiplied with some scalar multiple, that is equal to that scalar multiple times this plus that scalar multiple times the other vector, addition of those. So that's distributivity. We can repeat that once more in, not tomorrow, on Thursday morning, and go on with what is a spanning set and what is linear